My name is Joseph Wunderlich. I'm a professor of engineering, architecture, and computer science. And this is an overview of a computer architecture implementation at the gate level with an instruction set from a textbook long ago, but a foundation of many student and scholar of computing. And so you see in the middle of this picture here, which is a bunch of composite drawings from that textbook, is the basic architecture of this SC16H the data flow. And so you see a memory management unit, the MM there, and you see the L at the top and the ALU at the bottom, and some other different registers in there, accumulator and such. And then beginning at the top of this page, you see the top right here, how interrupts are handled, and the table right below that, all in purple, is how interrupts are handled with the action next to it in register transfer notation. So the PC is the program counter, and so you put the PC +1, it's a counter you increment. Remember, you always increment it because all probability you're going to need, because of locality of reference, the next sequential instruction. So you typically always do that. That's why the PC is a counter. And you can look at some of the other things going on there. So, and they show the states too. So, the states, there's a finite state machine that corresponds to this and how it is implemented, the sequencing of things. Then as we scroll down a little bit and look around, on the left side, on the middle of the page, is the ALU, the arithmetic logic unit. And you can see the different functions coming in from the right in green there, the summing and anding. And so you look to the right now and you see how IO commands are handled, and also in yellow, the register reference instructions, how the signals are created for those. When it's decoded, right, during the instruction pipeline, first phase is fetch, and then you decode, and then you create the control signals. That's what you're seeing here in circuit implementation form. Down, as you scroll down a little bit to the left there, you see some indirect and direct indexing. These are addressing modes, basic addressing modes, and how those are implemented. And then the bottom right-hand corner, you see the control flow for a SRJ, and in orange there's a subroutine jump, and how that would work. And so you can take a look at those. And then the very bottom corner is for the LAC, which is a load accumulator, and AND instruction and add instruction. Now, what you see here is the computer architecture defined by the instruction formats at the top here. The memory reference on the top left corner and the register reference in the top middle. Now, this is what we would be developing at IBM initially with our System 390s. Large-scale mainframe supercomputers, vector register units, and for IBM USA and IBM Germany. IBM's company, 450,000 people at the time when I was there 25 years ago. These are $1 million machines we were developing. Now, what you have here is a much simpler instruction set with, certainly less than 100 instructions. In IBM, we had 1,400 instructions, and we would start off with developing instruction formats as an architecture, and then we would simulate those architectures, simulate fully the architecture on an existing machine of a different architecture, and then we would develop a test kernel, the operating system, that would test that architecture with all the instructions and all the functionality, trying to stress the thing and create failures intentionally to see where the thing is weak and fix it. And then we'd go into VLSI circuit design with analog transients and all that, and auto routing written in HDL out of necessity, not for learning experience. But then we'd have that VLSI circuit we'd run on top of that, and then we'd fabricate a chip and run on top of that with a custom kernel and the APIs that the controlled randomness that they patented my ideas inside of IBM for topic of other discussion. So we have a simple machine here with the instruction formats defining the architecture. And then as you scroll down, you see, next to the different instructions, register transfer note, or it says function or description, the register transfer notation. And that's what we learn in assembly language class, and when, digital design 2 interfacing, assembly language and interfacing is, that you describe what you're doing with register transfer notation. Then you scroll down, you see more of that, and how those conditions, how you combine different signals with the instructions that are being decoded, and out of the first stage of the machine instruction cycle, the first state or the first phase of the machine instruction cycle, the first stage of the instruction pipeline, when you fetch, and then your next stage of decoding, and then now you're combining signals. Here you see in the pink and the yellow and the bright orange to create the behaviors that you need. And then once you know, the control signals, how you need to create them, then you see in the middle, the bottom middle here, a PLA, that's a programmable logic array. That's why we use rail logic in the introductory course in Digital Design 1. And so that's the way that looks. And then when you look on the right here, sideways, those are the finite state machines that we learn how to design when we do sequential circuit design. We do digital and sequential circuits. So sequential circuits yield finite state machines, or implemented with finite state machines. And that's how you actually execute the instructions. And that's what sets up the machine instruction cycle and stages of the pipeline. And so that's what you are seeing here for different modes of operation, general instruction execution, the bottom, and then the run mode. So you can take a look at that to understand better the details of the functionality. The next slide here is the timing. So you have a main clock circuit, and then you parse that into other clocks. You see the timing diagrams. You hear me always stressing how important it is to have timing diagrams with FPGAs and other devices when we're developing them, because what the reality is, when you create these circuits, and this is what we do inside of IBM, and the whole group, the whole research lab, for System 390 with 2,000 people in it, is we would create the circuits, and then you don't know how fast it will really go until you start just cranking up the clock, and then see when you get bit errors, and then you analyze it and you see what's going on, and you see, well, oh, I needed to not switch so fast here because I had to wait for the capacitance to charge up on the gates on this particular circuit before I had a clock edge come in. And then create an event that needs to then be activating other events, and that's how it works. These are essentially analog things as they're charging up with voltage, and then they become digital when they reach certain threshold levels. So if you don't give time, sufficient time, you're switching things too fast, you will have a problem. So that's why you end up with these odd clock rates sometimes. So we did inside of IBM, where they're not like an evenly divisible kind of thing. This is long ago, 25 years ago, we had 233 megahertz processor, which sounds slow now, but in 2020, but in the 1990s, that was pretty fast, the early 1990s, mid 1990s. So anyway, there's clocks. It's important to understand clocks and how to make clocks. And so you look at the computer design and everything in purple here, and the timing diagrams, and how critical timing. So some of my students have heard me preach about that many times, so I won't do it a little more here, but it's very important. It's critical in design. Otherwise, your simulation is just a cartoon. That goes. I taught simulation class too. I mean, if your simulation does not mirror real-time reality, then it's just a cartoon. And so, whenever I talk robotics or any kind of simulation, I make sure you have real-time code compared to the simulated code. You build a robot. I want to see the real robot moving around while the simulation's running on the screen, independent, and see, hey, does it look like what it should? So the timing diagrams will nail down your simulations and make sure that they're real for implementation. Otherwise, good luck. And the last slide here, looking at it sideways, going to the bottom left-hand corner, how the interrupts are handled. I won't go through all the details there, but you can take a look at that. And then in the middle is a DMA, that's direct memory access. Remember, freeing up the processor so I/O can talk to memory, and how to implement that. And then the I/O for input-output, the CPU and, versus the interface, and how that would be implemented with timing. And we build circuits like this in design and interfacing class. And this is why simulations or whatever devices we're doing, it's important to actually interface with the real world. That's why we do programmable logic controllers. That's why we do Raspberry Pis and Arduinos too for fun. And most importantly, when we're developing circuitry in an interfacing context, and why we learn assembly language on microcontroller, is because you need to know how to deal with the outside world, outside of your circuitry. You're driving things. You understand how to deal with that. The correct voltage levels coming out, and driving and sourcing the right amount of current. Pull up transistors and resistors. And pull downs to get that all working. And you see even the buffers in there too. In the middle, the bottom middle of the I/O on the rails coming off those little triangles. We do that. Tri-state buffers, learn how to hook up circuits. When you connect to a bus, you can't just connect a wire directly to the bus, especially if you have a million things connected to the bus. They're all sharing the bus. I mean, the bus is not a bus sounds like a thing full of people, right? The bus is actually the roadway itself and the way you connect to it, and you have to disconnect all the branches. You can't have them all feeding at the same time. We're talking about electricity here, so you can burn things out if you have everything activated on the bus at the same time. So you need tri-state buffers, and that's some of the reality. That's why we make physical circuits on breadboards, and why your simulations need to be as close to reality as possible. Whatever kind of simulation it is, logic simulation, your HDL stuff. When you're writing assembly language, you need to do I/O kind of stuff. So you have to really stay grounded in reality. Otherwise, you're living in a false reality of cartoon land, and then you can make anything happen. Unfortunately, the real world does not respond that way. And so, you must adapt accordingly. As the designers of the digital world, which is now consuming out of necessity and out of luxury, and controlling the physical world.